So in this video, we're going to work through solving some material and energy balances around multiple unit processes and processes that involve either recycle or bypass. So this first example comes from problem 4.38 in Felder, Russo, and Bullard textbook. I have shown here the image that is replicated from the textbook, but it's not labeled entirely as the textbook labels it. So what we want to do here is we're going to use this example that I have and start by fully labeling the flowchart. Before you go ahead and fully label the flowchart, I want to remind or just review the three different ways we can label a particular stream. So if we look at the stream shown here, and this is what I'm calling stream 2, we can discuss three separate ways that we can label this process. Okay, so the first way that we can label this process is we can give it an overall flow rate, so M2 in terms of grams per second, that's our unit for this process. And then we can write the fraction of each species. So we have species A, B, and C in this process. So we'll have the composition X A, we can call that XA2 grams A per gram, XB2 grams B per gram, and XC2 grams C per gram. All right, the second way we can label the process is very similar. We're going to have a total flow for this process, grams per second, and then we'll label A and B the same, so we'll have XA2 grams A per gram, XB2 grams B per gram, and now instead of writing XC, I'm going to apply the process constraint that the sum of the compositions equals 1. So the composition of C is going to be 1 minus XA2 minus XB2 grams C per gram. Finally, the third way we can label the process is by labeling the flow of each species. So we could have MA2 grams A per second, MB2 grams B per second, MC2 grams C per second. So you can see in each case we have, well, here we have 3 unknowns, in this case we have 3 unknowns, and in the first case we have 4 unknowns, but we have one additional physical constraint to relate the compositions of these 3. So we have the same number of unknowns regardless of the way that we decide to label the process. Okay, but I'm going to label this a certain way. If there's no information known about the stream, I usually find it easiest to label the stream in terms of the flow of each species. So we're going to call this MA2 grams A per second, MB2 grams B per second, and MC2 grams C per second. Okay, so what else do we have? This stream is fully labeled. This stream is fully labeled per the information given. In this stream, we know we have also A and B, so we should have, I'll call this M1, so MA1 grams A per second, and MB1 grams B per second. So finally, we just need to label the composition of this stream coming out. Okay, so we have A, B, and C that can exist in this stream. So we'll call this X, A, and this is stream 4 grams A per gram, XB4 grams B per gram, and then we will label this 1 minus XA4 minus XB4 grams C per gram. Now here I chose to apply the process constraint so that I didn't introduce another unknown to the system. And again, we labeled this stream in terms of composition because we knew the overall flow to the system. So we did have a known piece of information here. So now we have a fully labeled process. We have variables for the unknowns, and we have units on all parts of the process. So let's go ahead and do now a degree of freedom analysis. So we'll start with the unit 1. So if we look at unit 1, we have 2 unknowns. So I'll do my degree of freedom analysis right here. Unit 1, we have two unknowns, MA1, MB1. Okay, now the number of species that we can write, because we have two species, we can write two balances because we have two species, so we have two material balances. So two unknowns, two balances, that gives us 0 degrees of freedom over this unit. Next, let's look at this mixing point. Okay, we have MA1, MB1, MA2, MB2, MC2, so we have 5 unknowns. And then in terms of equations now, here we have 3 species. We introduced species C to the process. So we have 3 material balances. We have no physical constraints because we didn't label in terms of composition. So this would give us 2 degrees of freedom. And finally, let's look at unit 2. We'll call this 1, we'll call this 2. Around unit 2 we have 1, 2, 3, 4, 5. So again, 5 unknowns. And just like before, we have 3 species, so we can write, actually, I made a mistake. We have 6 unknowns. We have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So we have 6 unknowns. Now we have 6, or we still have 3 species, so we can write 3 material balances. So here, it looks like we would have 3 degrees of freedom. So finally, we can discuss the order in which we can solve this problem. So because we have 0 degrees of freedom around unit 1, we can first, our strategy, and again, this problem asks us to identify the strategy, not necessarily solve, but you could go ahead and solve it afterwards if you'd like. So our strategy is we're going to solve around unit 1, and by solving the material balances around unit 1, we can find MA1 and MB1. So that would take away 2 unknowns. Now that we know those 2 unknowns, the next thing we can do is solve around the mixing point, because we have now 2 fewer unknowns than we had previously. So in this case we would have 3 degrees of freedom, or 0 degrees of freedom, because 3 unknowns, 3 material balances. And this would allow us to find MA2, MB2, MC2. And finally, we can solve around unit 2. And by solving around unit 2, we can find XA4, XB4, and then M3. This would require a little bit of algebra, solving some systems of equations, but you can handle it from there. So that goes over how to draw and label the process, the degree of freedom analysis that allows us to solve the order, to tell us the order in which we would solve this system. Now conveniently we went from the left to the right, but keep in mind in many cases you may need to solve around the middle, towards the end, or the beginning. For our next example, we're going to look at problem 4.42 from the textbook. This problem deals with doing a separation of benzene and toluene using a distillation column. So in the picture you see here, I've drawn and labeled the process with all of the information that's given from the problem statement and nothing more. So there's a couple ways we can do this. One way is I could go and I could add all the unknowns, but instead of just writing the unknowns for each stream, I'm going to take a more thoughtful approach to labeling this process. Okay, so in the first case what we'll do is I'm going to look up by the condenser. Okay, so because we know it's a binary system, we have only 2 components. Because we know the composition of benzene, we also know the composition of toluene, 0.03 moles T per mole. Right? Now, we're told that we have complete condensation, so that means all of the vapor entering the condenser condenses to a liquid and then is split. Because all of it condenses and then is split, what we know is that the composition coming out of the condenser is the same as that going into the condenser, and the composition of these two streams are equal. Therefore, we know that we have 0.97 moles benzene per mole and 0.03 moles toluene per mole in this stream, and likewise for this stream, 0.07 mole B per mole, 0.03 mole T per mole. Okay, also we can do a very simple material balance. We're told that the stream sent back to the column is the same as the stream exiting the column, so each of these were labeled N1 in the problem statement. Therefore, we know that the stream entering the condenser must also be 2N1. That would be the total amount of moles in stream 1. Okay, looking at before we start solving the problem, I'm going to continue and label it to the best of my abilities. Okay, so now I'm going to come down to the bottom at the reboiler, and we're given these labels: YB in the vapor, moles of benzene in the vapor; XB, moles of benzene in the liquid coming out. Down here at the reboiler, it's only partial reboiler, and what that means is that the vapor and the liquid, so the vapor and the liquid are at equilibrium. So in this example, we're given the equilibrium relationship as a process constraint. Later on, we'll actually be able to solve this using simple equilibrium relationships. Okay, and we're also told that 45% of the feed to the boiler is vaporized, so we know the ratio between some of these streams. Okay, so let's go ahead and let's finish labeling on this. I'm going to call this stream 4. So this is going to be, N4, it's not N dot, it's just amount, moles. We'll call this stream down here N2 moles, and we'll call this stream N3 units of moles. Okay, also just to be consistent, or to come up with some different names, I'm going to call this XB3, and so I'll have 1 minus XB3 moles T per mole, and because I made this XB3, I'll make that a 3 right there. And also we have XB2, so we have benzene coming in, mole B per mole, and then 1 minus XB2 mole T per mole. Finally, 1 minus YB, and we'll call this stream 4 mole T per mole. Okay, so this should be B4, B2, B4. Okay, so now this gives us a properly drawn and labeled process. So first thing we need to do is we need to do the degree of freedom analysis to determine the order in which we solve this system. So I'm going to bring the paper up a little bit, and we'll start with the column. Okay, if we start with the column, around the column we have N1 as one unknown coming out. We have N2 coming out, N4 coming in, YB4, XB2, 1, 2, 3, 4, 5 unknowns. And if it's helpful to you, you may consider writing out the unknowns individually for the system. And then we look at the number of balances, as we can have 2 material balances because we have 2 species. Let's see, do we have any other? And I think that's about all. So this would give us 3 degrees of freedom. If you cleverly use some of the process constraints, you may be able to get rid of one of those degrees of freedom, but just for the simplicity and consistency, I'm going to leave it at that for now. So let's look at the condenser now. Okay, the condenser, we have N1 entering, N1 exiting, N1 exiting. So we have one unknown. Right, and then what else do we know? We have one process constraint that says 89% of the benzene in the feed of the column, and we actually know what that is. So we could consider that we do have the process constraint here. But the process constraint is somewhat limited by the fact that we know the exact amount of benzene here. So we know the exact amount of benzene that's here because it's 0.89, it's 89.2% of 50 moles. So we could solve around the condenser. Let's now look at the reboiler. If we count our unknowns around the reboiler, I believe we have 6 N3 XB3, N2 XB2, and N4 YB4. So we have 6 unknowns, and then we have 3 species balances, or 3 material balances. Okay, we have 1 equilibrium relationship. Oh, I said 3 balances, didn't I? Actually, we only have 2 balances because we have only benzene and toluene. So I'm going to correct that and say we have 2 material balances, B and T. 1 vapor-liquid equilibrium, and then we have 1 process constraint. So overall, we would have 2 degrees of freedom in the reboiler. Okay, so let's not forget the overall process. So we can do overall, and again, the overall degrees of freedom, we would be looking at the whole process. So entering is fully defined. Exiting, we have 1 unknown. Exiting down at the bottom, we also have 2 unknowns. So overall, we have 3 unknowns. Okay, we have 2 material balances for 2 species, and then we have 1 process constraint based on 89.2% of benzene in the feed comes out up top. So that would give us 0 degrees of freedom. So we can see here that we have some choices in terms of how we would solve for this system. Okay, so what I'm going to start with is, first we'll start with we'll call this our strategy. So one of the things I like to do initially is see if I can actually apply my process constraints. So if I use my process constraints, I know that the benzene, so the benzene exiting the system at the top of the column is, let's see, we'll say top, at the top of the column, if we do a balance on benzene, we have 0.97 times N1 equals, this is equal to 89.892 times the benzene in the feed, which is 0.5 times 100. Now all the units here are in moles. So again, I can use this and I can solve for N1. I think it comes out to be about 46.0 moles. The problem says do not solve, but we can go ahead and do this here. So that would give us N1 for the overall system. So now we have N1. So N1 is now known. So the next thing we might do is we could either, so we've entirely solved around the condenser. Everything on the condenser is known. So we need to decide again now, reboiler or the column. So I didn't really help us at all in terms of solving around the column, although I did get rid of one. I did get rid of one of the unknowns. So I would still have a few degrees of freedom left. Reboiler, I didn't help us at all around the reboiler. So overall I got rid of 1 unknown and 1 process constraint. So my strategy is I'm going to continue with the overall system. Okay, so the overall process, what may be easiest, again, I'm going to think about it before I start solving. is I can do an overall balance, a balance on species B, or a balance on species T. Because I know that N1 is 46 moles and I know how many moles are coming in, I can determine how many moles are coming out. So on the overall process, I'm going to do an overall balance, and so I know that I have 100 moles entering. So 100 moles equals, coming out of the top is N1, which I have solved for, 46.0 moles, plus N3. So here I can solve now N3 equals, again, I don't need my calculator, so I'll go ahead and solve this, 54 moles. Good. I have solved for now N3, so that means now I should be able to do a balance on either benzene or toluene to solve for XB3. So because it's given in terms of benzene, I will then do a balance on benzene. So now my balance on benzene is the benzene entering is 50 moles. So we have 50% of 100 is 50 moles. The benzene coming out is equal to 0.97 times N1, which is 46, plus XB3 times N3, which is 54. And then I get XB3 equals whatever I calculate that to be. So that helps me solve for N3 and XB around the reboiler. So now if we go back and do my degree of freedom, I have solved for the overall and for the condenser. If I look at the reboiler now, I have solved for 2 of the unknowns around the reboiler, so at this point I would have 4 unknowns. I still have 2 material balances, vapor-liquid equilibrium and a process constraint. So if I'm going to write out my strategy, the next thing I'm going to do is I'm going to solve around the reboiler. Okay, I have a few choices. I might limit, I know that from my process constraint that 45% of the feed to the reboiler is vaporized. So 0.45 times N2 equals N4. Okay, so that can help me eliminate one variable. And now once we go here, is we might have to think about it a little bit. We have our vapor-liquid equilibrium expression to relate YB4 and XB4, and then we have a balance on, so our other relationships is we have VLE, comma, balance on overall, B, and T, but we can only use 2 of these. So here I'm going to look for equations that have only one unknown in them. So if we go back to our equilibrium expression shown up here, we know that YB4 is in equilibrium with the liquid, so the liquid and the vapor exiting the reboiler have to be in equilibrium. Because we already solved for XB3 from the overall process, we can first solve, so my strategy is down here, first I'm going to use VLE and I'm going to get YB4. But I still have some equations, or I still have some unknowns. So if we look at the reboiler, the next thing I'm going to do is I'm going to do an overall balance, because I know the relationship between N2 and N4, and then I also know that N2 equals N3 plus N4. N3 is known. I can therefore get N2 and then N4. And finally I can then proceed to write a material balance on benzene to solve for the remaining unknowns in this process. Okay, so I'm going to stop that example here. You're welcome to continue and solve through and calculate out all of the unknowns for the system, which would be good practice, but instead of spending the time here, we're going to go on to the next example. For our next example, we're going to look at problem 4.45, which involves an evaporation crystallization process to produce potassium sulfate crystals. So shown in the image below, or in the image here, is a drawing of the process with the information that's provided. You can see here I only labeled on the process information that was given in the problem statement. Note up top, we're given the process constraint that 45% of the water fed to the evaporator is evaporated. And over here, I wrote the exit of the crystallizer in an interesting way. So we were told that the flow rate of the pure crystals, potassium sulfate, was 10 times that of the liquid that was contained, that the crystals were contained with. So you can treat this as effectively two different streams. One stream is the pure crystals, which is labeled as 10 M3, and the other stream is M3 kilograms per second. And this M3 would be that of the liquid, which is the saturated potassium sulfate in water. The flow rate of the crystals is 10 times that of the liquid in the stream per given by the problem statement. So you just have to be careful a little bit sometimes of how you set up and label the streams and how you designate the variables of each one with respect to the information given by the problem. Okay, so let's start by fully drawing and labeling the process. It's already drawn. Okay, so what we don't know entering the process is M1. So the flow rate entering in terms of M1, units of kg per second. Okay, we can also use the process constraint here to figure out how much water, 0.084 kilograms water per kilogram. All right, we're also don't yet know this, let's see, exit stream M3, stream over here, we're told it's 40% solids, so I can go ahead and label 0.6 kilogram water per kg, but this isn't necessarily known. We can call this M2 kg per second. So we have M1, M2, and M3. This stream up here, it's pure water, so it's fully defined. And we're also not given the streams entering the evaporator or entering the crystallizer, so those will have to have variables associated with them. We can call this M4 kilograms per second for the total flow rate, M5 kilograms per second total flow rate. But as I look at that, and maybe you look at that and you decide, I don't really like that much. Because remember, we're not given any information about this stream. So instead of using total flow rates, I'm going to label it a little bit, I think, more intuitively, which would be just the flow rate of each species in each stream. So M K4 kg per second potassium sulfate, and water 4 kg water per second. Same here, Mk5 kilograms K per second, Mw5 kgW per second. So now this shows me the fully labeled drawing in process. I have my variables, my units, my known information. Alright, so now I need to do a degree of freedom analysis. First, though, before I do the degree of freedom analysis, I want to try to see if I can use any of the process constraints or information that's given in terms of the problem. For example, do I have experimental data that I can use to determine the unknowns? Are there process constraints I can use to determine information? We're told that 45% of the water fed to the evaporator is evaporated. So that's 45% of the water fed to the evaporator is 175 kilograms water per second. So based on my process constraint, I know that 175 kg water per second equals 0.45 times M water 4 kg kg water per second. So I can quickly punch this into my calculator and solve for MW4 equals 389 kg water per second. Now, since I know the water coming in and I know the water coming out from the evaporator, I can also determine MW5. MW5 therefore equals 214 kg water per second. Okay, I got this information all from the process constraint. So what I'll do now is instead I'll modify my figure right here, cross out these variables, and instead write 389 kgW per second, 214 kgW per second. And I'll just indicate that I've used my process constraint, so I'll cross that off. Okay, so this is a good time now to do the degree of freedom analysis. And I will do that in this space here. So let's start with the overall balance, because a lot of times we forget the overall balance, or the overall process. So I have one unknown, M1. This is fully known. One unknown coming out, M3. I don't need to worry about any of this inside the process, only what enters and what's exits. So for the overall process, I have two unknowns. Okay, I have two species, so I can write two material balances. Therefore, I have 0 degrees of freedom on the overall process. So that could give me a good place to start. Well, let me just look at some of the other parts of the process. We have the mixing point. So here's the mixing point. At the mixing point, we have M1, M4, and M2. So we have three unknowns, and then here I have my two material balances, nothing more, and so I have 1 degree of freedom. Okay, let's move on to the evaporator. Evaporator shown here. Around the evaporator we have M4, MK5. So what is that, 2? Oh, 2 unknowns. This looks good. Okay, but let's look at, we have 2 species, so therefore we have 2 material balances. But wait, we have already used the material balance on the water to show the water coming in equals here. So even though we have 2 species, I can only count this as we only have 1 material balance left. So it's important to remember that if you use some information ahead of time, we can no longer use that balance again to solve for the unknown information. So I'm running out of space over here, but I have one more process to do a degree of freedom analysis on, so I'm going to move the paper up a little bit, and that's the crystallizer. On the crystallizer, we have 1, 2, 3 unknowns, and we still have our 2 material balances. So that gives us 1 degree of freedom. Okay, so now at this point, we've pretty much shown that there's really only one place we can start on this process. So as I start to outline my solution strategy, I can determine how to effectively solve for all of the unknowns in this process. Because I have 0 degrees of freedom on the overall process, I'm going to start there. So with the overall process, we have M1 and M3, which are unknown. Now, unfortunately, we can't have a single equation with a single unknown. So for our overall process, we are going to be stuck with 2 equations and 2 unknowns that we have to solve simultaneously. Okay? But the good news is once we solve for M1 and M3, we can move on to the mixing point. At the mixing point, we can start with the balance around the water, because we know the water in this stream, the water in this stream, and we can use that to solve for M2 by knowing the composition of water in this stream. Once we know M2, we can then do a potassium sulfate balance to solve for the flow MK4. So we'll do the water balance first at the mixing point, then either the K balance, or yeah, we'd use the K balance, not the overall balance, because that wouldn't help us. Okay, finally we go on to the evaporator. At the evaporator we only have one equation that we can use. The equation is going to be the K balance. We can use the K balance to solve for MK5. So let me just refresh on the strategy. I wanted to identify a couple more things. Two equations, two unknowns. This allows us to solve for M1 and M3. At the mixing point we use the water balance to solve for MK4, and then we use the potassium balance. No, I'm sorry, we use the water balance to solve for M2, and we use the potassium balance to solve MK4. Evaporator, we do the potassium balance to solve for M5, and then finally we go on to the crystallizer. And at the crystallizer, we can choose what we want to do first. We might start with the water balance because we should only have one unknown within the water balance. Water balance, we can use that to solve for M2, actually, which we already know. So actually we just need to do the K balance to solve for MK5. Okay, so now there's a couple questions that are associated with this problem, but now that we know the solution strategy, we can go through and determine all of the unknowns and answer any or address any of the information that's requested by the problem. For this last example, I want to briefly discuss one of the homework problems, which is problem 4.49. And I'm going to go about this in a slightly different way. I'm going to try to label information based on what I know about the process and add things as I know. So in this process, we have water, or makeup water, which is sent to a deaerator, and after the deaerator it's sent to a boiler, and that boiler goes to the heat exchanger to heat up a process fluid. Some of the water is lost as steam and other condenses and is recycled back to the process. Okay, so if we know what happens in this process, at the boiler, for example, only steam is evaporated. Okay, so in the makeup water coming in, we're told that the makeup water has 1 kilograms of impurity per 2,000 kilograms of water. And so we're going to go and label this process on the basis of 2,000 kilograms of makeup water entering the system. So if we do so, we can start by saying we have 2,000 kilograms water, and then based on the process constraint we know that we have 1 kilogram impurity per kilogram water. Alright, now again we have water that's going to be recycled back, which we don't necessarily know what that is. Going from the deaerator to the boiler, again, I know that I have 1 kilogram I. All the impurities goes this way. I don't know how much water is there because we mix some. Okay, and then coming out of the boiler, we know that all of the I, all the impurities comes out as blowdown. So we have 1 kilogram of I that comes out there. Okay, but we're also given a process constraint about the boiler in that 350 kilograms of water comes out with per kilogram of I. So we know we have 350 kilograms water. Okay, so what else do we know? We know that 76% of the water that enters the heat exchanger is condensed and recycled back to the deaerator. So let's think about how I can label this carefully. We don't know the water from the deaerator to the boiler, so I'm going to just call that M1 kg water. We also don't know how much water goes from the boiler to the heat exchanger, so I'm going to call that M2 kg water. The temptation might be here to write M1 minus 350 kg water, but again, let's not do our balances on the flow chart. Okay, now lost steam. Here we know that 76% of the steam entering the heat exchanger is condensed. So rather than making a new variable, I'm going to go ahead and just call this 0.76 M2 kg water in this stream, and therefore I would have 0.24 kg water lost as steam. Okay, so I did a little bit of a different way of labeling this process, but I was consistent within the process constraints, knowing all the iodine or all the impurities goes through the process in this direction. Now the tough thing going forward though is I need to remember a couple things. Around the deaerator, around this deaerator right here, I already did my iodine balance, so I only have one material balance left. Right? Around the boiler, still again, I already used my material balance, or my impurity balance, so left here I only have one material balance. Around the heater, we only have one species water. I use the process constraint that 76 cycles back, is recycled back, but then I also use my material balance to get that 0.24 water comes out as steam. So around the heater I actually have 0 material balances that I can use. Okay, so as we try to be clever in terms of labeling our process, we also have to be aware of the fact that we may end up using the balances. So again, when I do my overall degree of freedom analysis on the system, I need to consider that. So remember, you want to think about what overall process, look at the degrees of freedom for the overall process. The deaerator, the boiler, and the heat exchanger. So after you do the degree of freedom analysis, you can identify where you can start to solve the problem, the order in which you can solve it, proceed to go through and calculate the unknowns. Once you know the unknowns for the process, you can address any of the questions that are asked in the problem statement. So that's all for today.